Hello everyone, we're going to start our first lecture, and in this lecture we are going to give some introduction of differential equations. What types of differential equations we have, how to classify them, what are the methods to visualize solutions. We're not going to really solve any differential equations in this lecture. I'm just going to show you how they look and like where to look if you find certain differential equation. So generally speaking, I'm trying to summarize the whole chapter 1 from your book. But because I'm going to mostly do classification, I'm going to label it as 1.3. That's where they do classification in the book. Classification of differential equations. Well, first, differential equations are equations with a derivative. What does it mean? Normally, guys, in algebra, we do have equations looking like this, for example. 3x to the power of 5 plus sine of x, for example, plus, I don't know, e to the power of x equals to 0. This is equation about variable x, right? Solution of this equation is x, which turns this equation into a true statement. So left side is equal to right side, right? This is algebraic equation. Differential equation is going to be not about a certain variable you can calculate and plug into equation, but about a certain function. So instead of x, you can have a whole function. Equation is going to look similar, but it's going to have a derivative. We are going to first give a general classification of differential equation. So this is algebraic equation. Differential equation can look like this. For example, y first derivative of x plus, I don't know, 3y of x equals to 0. Here you have first derivative of function y of x, which is unknown, plus 3 of this same function y of x supposed to be equal to 0. Solution of this equation is going to be not just one number or a set of numbers. Solution of this equation is supposed to be a whole function y of x. Solution is y of x, whole function. You plug it into equation and it's becoming a true statement. Okay, it's not necessary that it's going to always have a first derivative, can be any derivative. So how do we divide differential equations in the world of differential equations? Well, there are two big types of differential equations: ordinary differential equations and partial differential equations. For ordinary differential equations, we are going to call them ordinary differential equations. I'm not going to write down differential equations every time when I say differential equations. I'm going to put DE, differential equations. O means ordinary. Ordinary means equations where y, the function, depends on one variable. I'm going to put here one variable. Can be x or t or any other letter, but that's going to be just one variable. A good example of differential equation with one variable looks like this. Y, second derivative, can be of, for example, x plus omega square y of x equals to 0. This is differential equation about function y of x, right? You see second derivative over here, so correct function supposed to turn this equation into a true statement. Only one variable here is defined inside of the function, one independent variable x. Normally, we are going to either assume that variable is t or x, and lots of times people are not going to specify variable if the differential equation is about the function y. They're just going to allow you to use any name for the variable. Okay, so solution here is going to look like one function y of x, right? Another type of differential equations is going to be partial differential equations. For partial differential equations, I'm going to write down P, D, E. partial differential equations? Well, obviously, if ordinary differential equation has one variable in a function, partial differential equations are going to have several variables, and more, they are going to have partial derivatives. I'm going to write down several variables. Well, I'm going to give an example of partial differential equation, and that's going to be the wave equation. A square u x equals u t t. What is the function here? Function u. How many variables we have? U depends on two variables, x and t. What is ux? Ux is partial derivative of u of xt by dx. Remember from calculus 3 that if function depends on several variables, we can take partial derivatives, right? Well, xx means that second derivative I'm going to write down. So uxx is going to be d second derivative u by dx2. Well, any equation with partial derivatives and several variables is going to be called partial derivative equation. Besides these two big subdivisions on ordinary and partial, we can have more than one equation solved together. For example, you combine two ordinary equations and solve them together. They are going to be about same variable x, but they're going to have two different functions. For example, this is function y1, and you create a similar equation with function y2, but slightly different parameter omega, for example. There are going to be two solutions. Not necessarily they're going to be equations about different functions explicitly. For example, first equation for first function and second equation for second. They can kind of interchange the functions. For example, here, somewhere, the function is y1 here and y2 here, and they mix together. The combinations of equations like this are called systems. And systems of equations can be ordinary and partial. I'm going to put the one word systems here. We're not going to dedicate lots of time to systems of equations, but we are going to meet systems sometime. So I don't know where to put systems. Systems can be ordinary or partial. I'm going to write down systems. I'm going to write down that has more than one equation. System has more than one equation. Okay, so we now want a big classification of differential equations. Actually, there are the whole branches of math which are working explicitly with ordinary differential equations or with partial differential equations. More important for differential equations is order of differential equation. I'm going to define order of differential equation. What is order of differential equation? Order of differential equation is an order of the highest derivative. In equation. Well, for example, I'm going to write down equation of, let's not say what order, try to guess. Well, this is typical differential equation, right? Is it ordinary or partial? Well, if you don't see any partial derivative signs like this, a little index is xx or tt, and you just see bars over here like 1, 2, 3, 1, 2, and there's no more, right? You expect to have ordinary differential equation. Now, if you look for the highest derivative here, it's going to be this one. It's going to be a third derivative, right? So we are going to have a third order. Third order, right? The highest derivative is going to give equation of a third order. What else? Well, equations, differential equations can be linear or non-linear. And like any of these equations can be linear or nonlinear. So it's not like subdivision of these divisions. That's actually like another division, another way to differentiate that between equations. So linear or non-linear differential equations. So what is the difference? Well, we're going to start with non-linear. We're going to define what are linear differential equations and then say that whatever is non-linear is going to be called non-linear. Okay? So if your equation looks like this, a0 of t, y, and derivative. If you do have a little number in a little parenthesis on the top of the function, this is not the power of the function. That's going to be actually order of the derivative. For example, here it's nth derivative. This is a function which depends on t. We are assuming that we have ordinary differential equation with variable t. So if your ordinary differential equation with variable t looks like a polynomial, similar to a polynomial, I'm going to write down several terms. Sorry, multiplication, and then equals g of t. I don't know if you see well on the margin. Okay, if your equation looks like this, I'm going to put in parentheses polynomial a0x to the power of n plus a1x to the power of n minus 1 plus an, well, let's say x, I think I'm supposed to put n minus 1 here, n minus 1 here, an, something like this, equals to 0, for example. So if your equation looks like a polynomial, but instead of x to the power of n, you have orders of derivatives like n's derivative, n minus 1 derivative, and like the function itself, which is kind of 0 derivative. And instead of the constant coefficients, you have functions, but that's like how it looks. The equation is called linear. So what we have, all y's are sitting by themselves. They are not mixed together. And y's and t's are not mixed together in the same function. For example, here a0 depends only on t. It does not depend on t and y. Then we do have a linear differential equation. Everything what is non-linear is going to be called non-linear. Let me give you an example of a linear differential equation and non-linear differential equation. Linear. Well, I'm going to just use example from the top. Y second derivative plus omega square, y equals 0. This is linear differential equation. You see the coefficient of the second derivative is 1, the coefficient of a first derivative is 0, the coefficient of the function itself, which is kind of 0 derivative, is omega square, equals to 0. This is typical linear equation. Is it necessary to have constants in front of the derivative? No, it can be a function here. For example, sine of t. It can be a function here, e to the power of t or something like this. But it's still going to be counted as linear. A typical non-linear differential equation. Looks not much different, but you will see the difference. Why this one is nonlinear? If you compare it to a polynomial, this is supposed to be a coefficient, right, which is supposed to depend only on a variable of a function. Here we do see x, so y depends on x. But actually, this is not a function. It's supposed to be a known function, right? It's unknown function y. So this factor is turning this equation is nonlinear. Well, you can say that derivative is turning in nonlinear too. If you put it in front of y instead of y, it's going to be like this. Okay? Okay, so now let's talk about solution. What is solution of differential equation? So we talked about order, we talked about what kind of derivatives we can have. What is solution of differential equation? Well, usually, guys, solution of differential equation is defined on interval, and we are going to call function phi of x, or in the book, sometimes they are going to put phi of t, depending on what is your variable in the equation, phi of x or phi of t. Solution on interval I, open interval I from A to B. Well, what are A and B here? They can be just real numbers, they can be infinities. So just like the cover for the interval. Interval is where solution is going to work. What solution must do to differential equation? Solution must turn differential equation into a true statement. Turns differential equation into a true statement. Well, for example, I'm going to show you equation and its solution. Second derivative of y plus y equals 0. Typical differential equation. What is the order? Order is second order, right? Because it's a second derivative. Linear or non-linear? Looks like it's linear, right? All coefficients are just constants. They are not even functions. Partial or ordinary? Looks like ordinary. There are no partial derivatives. Again, partial derivatives in the world of differential equations are usually going to look like little indexes xx, tt. They're going to be different from just differentiation sign. Okay, so proposed solution. Well, I'm going to call it y equals cosine of t. Proposed solution. How do we know that this is solution? You guys don't know. I'm just telling you that can be a solution. We're not learning how to solve differential equations in this section. We are learning some ideas which we are going to use later. Some definitions, how do we name stuff in differential equations. So don't worry too much why I'm proposing a totally arbitrary function as a solution. Trust me. We are going to take this solution and check if it turns our equation into a true statement. To do this, well, we do have the function, right? But differential equation has a second derivative. So I'm going to differentiate my solution. So y prime of cosine is negative sine. Still remember this, right? And if I differentiate negative sine, I'm going to get negative cosine of t. Now I'm going to plug it into differential equation and get minus cosine of t instead of second derivative, right? Plus cosine of t equals 0. You see that these two cosines are going to cancel and we are going to get 0 equals 0, true statement. True. Now it's solution. So it's not just proposed solution, it's a solution. Okay? Well, now when you know a little bit about differential equations, you can ask some questions. And questions are mostly about solutions. So, question number 1. Does it always exist, a solution? Or we do have equations without solutions? Question number 2. Is this solution unique? So do we have only one solution, or there are like 5 more, or like how many solutions we have? And the last question, which is maybe most essential, is how to find these solutions, like methods. Well, guys, mostly in this class, we are going to answer question number 3, how to find solutions. We are going to dedicate a little time on existence of solutions and uniqueness of solutions. But it's not going to be too much because this is a heavy theory. And if we concentrate on it, we are not going to learn techniques of solving differential equations. And I think it's more important to have on your hands some techniques of solving differential equations for future science projects you are going to have for your physics and chemistry and biology classes. You better know how to understand solutions of differential equations. And if you are interested, you always can read the theory in the books. Usually theory of differential equations is complicated, so you will need to look in slightly more advanced books than our textbook to have better theory. We are going to have some theory, a little bit, but it's not going to be that much. Okay. What other interesting stuff we're supposed to know about differential equations? Well, we started talking about solutions, right? And we asked important questions. I'm going to write them down. So let me again go over important questions we usually answer when we meet a problem with differential equation. Do we have a solution? Does it exist? Is it a unique solution? And how to find this solution. And again, in this class, we concentrate mostly on how to find solution. We are going to solve mostly problems for which solution exists and it's unique. We are going to have a little theory on this first about these first two questions, but in general, theory is complicated. Let's continue with classifications and talk about explicit versus implicit solutions. So far, guys, you've seen one solution of one differential equation, right, which I checked. It was like y second derivative plus y equals 0, and I was checking cosine. Solution like this is called explicit solution, when y is sitting on one side and function of x or t sits on another side, which is a solution. Let me remind you a little bit about implicit and explicit functions. For example, explicit versus implicit. Y of x equals x cubed plus 5. This function is solved for y. So y, dependent variable, sits on the left side. X and like combinations of x, mathematical expressions with x are sitting on the right side. This is explicit function. Solved for y. If you have something like this, y squared plus x squared plus xy equals 5, the function which is given by an equation which is not solved for y is called implicit function. Not solved for y. Solutions can look like explicit function or they can look like implicit function. And they're not good or bad because of this. Sometimes it's impossible to find solution as explicit function and only implicit solution exists. Let's consider a couple of examples. For example, I'm going to consider one example of explicit solution and one example of implicit solution. So, explicit. Well, I'm going to consider again a very simple equation. Y prime equals 3y. You see it's linear equation. If you move everything to the left side, you are going to have equation of first order, linear, right? I'm going to propose a solution. Y equals e to the power of 3x. Proposed solution. Well, again, for right now, it's not very important why I propose this solution. I'm trying to explain a different idea. I'm trying to explain you like what is the difference between implicit and explicit solution. This is explicit solution, right? Because y sits on one side and everything about x, a function e to the power of 3x, sits on another side. This is explicit solution. I'm going to check it by substitution, so I'm going to differentiate it. So y prime here is going to be 3e to the power of 3x, right? I'm going to plug it into equation 3e to the power of 3x equals copying this 3 and copying the function. Do you see? True statement. So that's an explicit solution. Now, to get implicit solution, I don't want to give you an equation and solve it, because solving equations with implicit solutions is a little bit harder than just like propose a solution and just substitute it. What I'm going to do, guys, I'm going to use implicit function and differentiate it and obtain implicit equation. And because equation was obtained from the function is going to be a solution of this equation. So implicit. Well, let's consider equation of a circle. X squared plus y squared equals 4. Everyone remembers that's a circle with radius equals 2, right? Centered at origin. Why do we need implicit equations, actually? You see that circle is not a function. So if you want to describe it as a function, you will need to do it through two functions, the top part of the circle and the bottom. If you want to do one function, it's supposed to be given implicitly like this. Because, well, you see the circle does not pass vertical line test. What I'm going to do, guys, I'm going to differentiate this equation. I'll just differentiate it term by term. So, for example, I'm taking x squared and derivative of x squared is 2x. For y, because y is a function of x, it's going to be a little bit more complicated because it's like a composition, right? Composition of y squared, squaring function, over function y of x, which we actually don't know, right? So I'm going to differentiate first a squaring function. Usually when I differentiate y squared, I'm going to get 2y, right? But because y is not a variable by itself, but a dependent variable, depends on x, I'm going to also have dy dx here. Derivative of 4 is 0. And you see, we got equation. And solution of this equation is going to be this function. And the function is going to be implicit function. Can we kind of, looking at the equation, tell whether a solution is going to be explicit or implicit? Most likely no. Because sometimes you just solve it and you get explicit solution. Sometimes you cannot get explicit solution. In this case, you can get explicit solution, right? Just like consider two parts of a circle, top and the bottom, and they're going to give explicit functions. But there are some equations which just don't have explicit solution. Transcendental equations mostly don't have explicit solution. So we are going to accept implicit solutions. This implicit solution is going to usually look like a function of x and y, either which equals to a constant or which equals to 0. I'm going to move 4 to the left side and write it down like this. And then I'm going to call this function g of xy equals to 0. So function g of xy is implicit solution. If you plug it into your equation, and it's going to give you a true solution. Well, here I'm not plugging it in because I already kind of got equation from differentiating of the function. So function is going to be a solution. But we are going to practice with this a little bit later with finding solutions of implicit form. Okay. What we need to know also, another stuff, more definitions, and then we have a little practice. Initial value problem. Well, before we discuss initial value problem, I want to return back to my equation with explicit solution. Very simple equation, right? Y prime equals 3y. We already know that y equals e to the power of 3x as solution. Do we have more solutions? How about y equals 5 e to the power of 3x? Is it going to be a solution? Well, let's plug it in. So y prime, in this case, it's 5 by 3 to the power of 3x. So I'm going to plug it in. 15 e to the power of 3x, here 3, and then my function 5 e to the power of 3x, and you do see 15 here, it's solution 2. Wow, actually any number can be multiplied by this function and give you a solution. In most of the cases, in actual physical problems, it's not like we have infinitely many solutions. Usually if something is moving, it's not going to move by infinitely many trajectories or with infinitely many functions of like velocity of time. It's going to usually have a unique solution. What does it mean, guys? Well, by the nature of differential equation, it needs an additional condition to check which of all these solutions is going to work for a specific problem. This is called initial condition. So for equation of the first order, initial condition is going to look like this. Initial condition. Well, you set up that y at a certain moment of time. Well, here we have x, at certain x, for example, at x equals 0, equals to a certain number. I don't know which number to choose. Let's choose number 5. How about this? Let's choose number 5. Initial condition means that you want to sit just on one of these infinitely many functions which are appearing from solving differential equation. Well, let's check which one is going to satisfy, which one of these two is going to satisfy this initial condition. Well, I'm going to start with first one. I'm going to plug it x equals 0 here and find out that y of 0 for the first one is e to the power of 3, 0. E to the power of 0 is 1, so y of 0 is actually 1. Does not fit to us, right? How about the second one? Y of 0, 5, e to the power of 3 by 0. Here we are going to have 5. So our second solution satisfies our initial condition. Now, when you combine differential equation together with initial condition, we are going to get very important differential equation problem, which is called initial value problem. Initial value problem is going to be labeled as initial value problem. Most problems which we solve in real life are initial value problem. If you do calculate something, usually you do know how the system was looking somewhere initially, like at the first moment of time, or like how it looks at here, for example. Do we have any other value problems? Yeah, guys, we do have boundary value problem. We're not going to dedicate lots of time in this class to boundary value problem because it's a totally different branch of differential equations, which shares some theory with this part, but also has lots of additional theory. I'm going to just write down that it exists, and eventually we are going to meet it in this class. But for right now, we are going to concentrate on initial value problems. Boundary value problem. Boundary value problem. What is boundary value problem? Well, you know, sometimes it's important how the system started to move. Sometimes it's important that certain points of a system are fixed at a certain position. For example, imagine you have a string on a guitar. And, well, I'm not very good in drawing, so I'm going to draw something like a guitar. Okay? And the string on a guitar. Usually, you know that the string on a guitar is going to be fixed at 2 positions. And you kind of deflect the string, and that's going to produce sound. Actually, string is going to oscillate. This is going to be called boundary value problem, right? Because there are 2 points which are going to always sit in place. And everything else is going to move, but these 2 points are fixed. These are going to be like boundary conditions. Again, we are going to meet them at the very end of our class. So for right now, we're going to concentrate on initial value problems. Okay? One more thing we'll need to know before we start solving those differential equations is how to visualize solutions, or how to kind of predict a little bit behavior of the solutions without actually solving anything. Well, we actually can do this in the theory of differential equations. It's possible to use computers or just like calculations. So what we have, a special method which is called direction fields and isoclines and integral curves. Well, before I talk about direction fields, I'm going to just give you an example of direction field. That's going to be a better way to explain what is direction field. But usually, these both methods are used to visualize solution. Okay, let's consider example. Equation y prime equals x plus y. So very simple differential equation. If you move everything to the left side, you are going to figure out that that's the first order linear differential equation, ordinary. What we can do with this differential equation? Well, basically, guys, derivative here, it's solved for the first derivative, right? First derivative sits on one side and everything else on another side. What we can do, we can build a field of derivatives. Remember that for graph of a function y of x, derivative is a slope. Actually, we can build a field of slopes of possible solutions. How are we going to do it? Well, we are going to create a little table. Here I'm going to put x, here I'm going to put y, and here I'm going to put y prime. So what I can do, I can use x equals 0 and y equals 0, plug them in over here. And I do know that for the point where x equals 0 and y equals 0, y prime is going to be equal to 0. So the slope of the function is going to be equal to 0. Now I'm going to use x equals 1 and y equals 0. Plug it in here. 1 plus 0 is 1, and I know that at the point where with coordinates x equals 1 and y equals 0, the slope is going to be equal to 1. So actually tangent line to the curve is going to be under 45 degrees. Remember that the slope of a curve, it's a tangent of the tangent line, right? Well, I'm just going to use one more, 2, 0, and plug in 2 and 0 here. I'm going to calculate it. It's 2 here, and then use slightly different points. 0, 1. Let's change now y. Well, 0, 1 here is 1. 0, 2 here is 2, right? And I'm going to just use 1.11. If I put 1, 1 here, I'm going to get 2. How are we going to use it? Well, I'm going to draw a little graph, and then show you the graph generated by GeoGebra on the computer. So over here is x and over here is y. So how many points I have? 1, 2, 3, 4, 5, 6 points. At point 0, 0, the slope of my tangent line is going to be 0. I'm going to draw it as a little bar like this, like a little line with slope equals 0. At point 1, 0, this is point 1, 0, right? I'm going to have slope equals to 1, so I'm going to graph it like this. Slope equals to 1 means that the tangent line is under the angle 45 degrees. At point 2, 0, I'm going to have a higher slope. Slope equals 2. Well, I don't know what angle is going to be. It's supposed to be around 50 something, but I'm going to just draw it bigger. What do I have at 0, 1? Well, again, 0, 1, that's x equals 0 and y equals 1, and the slope is 45 degrees. And the 0, 2 is going to be point over here. The slope is going to be a little bit higher. And at point 1, 1, which sits over here, the slope is 2 again, parallel to this. Well, considering my limited ability to do the points, I just made up 6 points, right? But normally on a big computer, not on a big computer, but on any computer, you can generate like 100 of points and have the idea how the slopes of the curve are going to behave. It's not going to give you a solution, but it's going to tell you like how solution behaves at infinity, nearby certain points. And sometimes it's good to know how it happens. Well, I produced a graph generated on GeoGebra. They do have direction fields, and you just enter your differential equations. It's going to graph you direction fields. My suggestion, try it at least once. So you can look at the picture for a second. And after looking at the picture, we are going to move to another method of graphing. You know that graphing using the coordinates and the points is a little bit too hard because we just like spend like 10 minutes and we graph just 6 points. There is a faster way to do this, and this way is called isoclines. It doesn't work in every case, but in this case it's going to work. If you look at this equation, I'm considering the very same equation, and you set up x plus y to a constant, I don't know, any constant, x plus y equals to a constant c. C can be 2, 5, whatever you want. Then y prime is going to be a constant too, because if constant sits over here for any x and y, then it's going to be the same slope for all this x and y. What does that mean? Let me show you. For example, I'm setting up the constant x plus y equals to 1. So everywhere where x plus y is equal to 1, the derivative is going to be 45 degrees. So it's going to look like this. What are the points where x plus y equals to 1? Well, they sit on a straight line, y equals 1 minus x. Well, let me do another graph. I'm going to graph below this one, okay? So I don't move to a different page. And you see similarity between these two graphs. So y equals 1 minus x is going to give me a line looking like this. I'm going to graph it as a dashed line, because if I have it as a solid line, then you won't see the tangent lines anymore. That's my first isocline. Isocline is a line where derivatives are all same. Now, I know that derivative at every point of this line is equal to 1, so it's 45 degrees. So I can draw as many of these 45 degrees slopes as I like this. So all these are going to be slopes, and they're all going to be equal to 45 degrees. If you go back to my previous graph and graph this isocline, you're going to see that it's correct, that 45 degrees here and 45 degrees here, exactly like over here. But you see, I just did one line and I got as many these slopes as I wanted. Now I'm going to set it to 2, just for one more, and then kind of, computer is going to generate the same field, no matter how I obtain it. But on paper, it's much easier to draw the lines. Y equals 2 minus x, right? You move x here. And my next line is going through the 2, and that's negative slope going to go like this, right? On this line, all slopes are like a little bit higher, like 2, right? I don't know how many degrees is this, but a little bit higher than 45 degrees. And you see, almost for free, I get like 10, 15 slopes right away. Where this line is going to be on my previous graph. The line sits over here. You do see that the slope is equal to 2 here, 2 here, and 2 here, but it's much easier when you draw the line just to draw the slopes, right? Instead of calculating 6 points. Well, we can continue and do as many as we like. And that's a faster way to get the picture of the graph if you don't have a computer. Of course, computer is always going to be much faster than this. And the pictures which are produced by computer is going to be same, of course, because the same equation produces same direction field. Now, guys, what I want you to do, I want you to try to graph these direction fields, maybe using isoclines or points as you like. And I'm going to give you 3 problems to solve on your own, and wait a little bit and show you solutions, okay? Problem 1, y prime equals 2x plus y. Problem 2, y prime equals x over y. And problem 3, y prime equals minus 2y. So for all these 3 functions, I want you to kind of try to graph at least few direction field lines, okay? And what you can do at this point, you can stop your video, try to graph at least like a couple of isoclines. And I understand that it's not easy to graph the slopes equals 1, 2, 3, and so on, but, well, a couple of isoclines is very possible, right? And then I'm going to show you the pictures generated by GeoGebra and my solutions too, of course. So I'm going to count to 3 and continue solving, but you can stop your video and try to do these problems on your own. So 1, 2, 3. Solutions. So for the first problem, we're going to have a constant equals 2x plus y, from where y equals constant minus 2x. Basically, that's a bunch of straight lines. Just here we had minus x, and here we are going to have minus 2x, so they're going to be more inclined. I don't know where to graph it. Okay, I'm going to graph it right over here. I'm going to graph 2 of them. So it's 1. If constant equals to 1, we are going to have something like this. Okay. If constant equals to 1, then derivative equals to 1, and I'm going to have 45 degrees. I'm not going to do more of them because I'm planning to show you the GeoGebra direction fields. Okay. For problem 2, For problem 2, y prime equals x over y. If we set it out to a constant, we are going to have y, let's do x over y equals to a constant, and then x equals cy, and then y equals x over c. Well, y equals x over c, it's actually also a bunch of straight lines, but they are not going to be shifted from the origin. They will go exactly through the origin. If you set x equals to 0, y will be equal to 0. And they're going to have different slopes, right? If you have 1 here, it's y equals x. If you have minus 1 here, it's going to be y equals negative x. I'm going to graph only 2 of them. C equals 1 and c equals negative 1, because I don't know how to graph slopes different from 45 degrees. So c equals 1 is going to give me isocline y equals x. C equals negative 1 is going to give me isocline y equals negative x. Y equals negative x. Now I'm going to do the slopes. So here the slopes are 45 degrees. Actually, 45 degrees is exactly same as my dashed line. I don't know how to graph, like how to show that these are actually my inclined slopes of the derivatives, but they are going to match the line. Slope of negative 45 degrees is going to look like dashed line too. So actually, if you compare it to the picture from GeoGebra, you're going to see same. So these two crossing lines are going to have 45 degree slopes, and they are lines, and at the same time they are going to be direction fields. Okay, and the last one, number 3. Number 3 is y prime equals minus 2y. So if I set it to the constant, I'm going to have y equals constant over negative 2, right? Well, so what is this? That's a bunch of horizontal lines, right? If you see a constant, if you set up constant equals negative 2, you are going to get y equals 1. If you set a constant equals 2, you are going to get a constant y equals negative 1. So you're going to have a graph looking like this. First one, negative 1, second one, right? So on the first one, the slope is equal to 1, right? Remember, this is like the number over here, the value of a constant. Oh, that's not negative, not 1, but negative 2 actually. The slope is negative 2. The constant is negative 2. Negative slope is kind of opposite direction, not 45 degrees, a little bit more. Here the slope is 2, something like this. And that's like at least like 2 lines with lots of like direction of the derivative. And you graph more of them, you are going to have a higher slopes, right? Like these slopes are going to be like turned this direction, and the slopes below axis are going to be turned this direction. Okay, I think that's all. I have like 3 homework problems, or 2 homework problems, I don't remember actually assigned. But normally for this section, because you are not going to learn anything how to solve anything, you can just draw the pictures like this, use GeoGebra to see how equations are having their solutions. You can try to classify any differential equations you see, like in the book. Just open the book in the middle and just point at differential equation and okay, this is partial differential equation or ordinary differential equations. What is order? Whether it's linear or non-linear. You cannot predict the solution whether it's implicit or non-implicit. Okay, that's all for section 1.3, or better say for chapter 1. Next lesson we are going to move to chapter 2.